Live now on YouTube. All right, welcome everybody. This is the June meeting of the RASC-Kingston Center, and I can't believe it. It's like almost summer. I don't know where the last 6 months went, but wow, they've gone by fast. I want to welcome all new members and returning members and anybody that's on YouTube. Plus, I also want to introduce our executive who is online here. Susan, who is our treasurer. We have Kevin, who is the web team and editor of our newsletter. We have Francesco, who's our librarian. We have, I don't see Rick online yet, who is our past president. We have John Hurley, who is the National Council rep for Kingston. And we have David Levy, who is our honorary president. So welcome, everybody. We have a few executive members that aren't here right now. Lori, who's our vice president, Acer, who is our secretary, but hopefully they will show up in a bit later. So the RASC-Kingston Center is celebrating its 60th anniversary this year. So if you have some history, I'm talking particularly those who have been members in the long past of the RASC-Kingston Center, could you please send it to kingston@rasc.ca, as we would like to get something together. If we can't get together or physically, then at least we can actually do something virtually, and we would like to have a celebration. On the national membership side, the database is up and running, and the center portion is now supposedly going to be hooked into those members of the executive that will be using it, but I haven't heard anything from the national office yet. And Moon at Noon is on Thursday. So tomorrow at noon, they will have a live presentation on observing the moon. So you can register for it off of the RASC website, or you can watch it on YouTube because it will be online. Now I'm looking for Rick Wagner. Is here? Okay. David Levy is going to start us off with a poem and an introduction. David, you're up.
Well, thank you, Kim, and welcome everyone to our Kingston Center. As soon as you mentioned about the 60th anniversary, it brought back a lot of memories for when I was an active member of the Kingston Center before I relocated to Arizona. I remember knocking on the door of Vibert Douglas's apartment and talking with her for several hours and becoming good friends with Vibert Douglas. And over many, many years. In fact, she was invited to be on my master's thesis committee. And she actually was really very helpful and very useful for a thesis that really had almost only marginally to do with astronomy. But I kind of made it work, and so did she, and it worked out very well. For my quote today, we're going to go all the way back to William Shakespeare, because I think if he were here, he'd want to know all about tomorrow's eclipse of the sun. And as he sits down to write King Lear, possibly his greatest play, he has Gloucester say these words: "These delayed eclipses in the sun and moon pretend no good to us. Though the wisdom of nature can reason it thus and thus, yet nature finds itself scourged by the sequent events. Love cools, friendship falls off, brothers divide." And then Edmund jumps up, his illegitimate son, and he says, "This is the excellent foppery of the world, that when we are sick in fortune, often the surfeits of our own behavior, we make guilty of our disasters the sun, the moon, and the stars, as if we were villains on necessity." I really think that if Shakespeare were right here, he'd say, "I just want to see the eclipse with you people." And now back to you, Kim. Thank you.
Thank you, David. That was excellent. I know some of us are going to be getting up early to try and observe what we can see of the eclipse tomorrow, but we'll have more on that later. Hank Bartlett will be giving us a little bit of information. So Rick Wagner is going to introduce our guest speaker, Dr. Doug Johnstone, tonight. Rick.
Thank you. I ran into Dr. Johnstone at the recent CASCA meeting. In fact, he ran into me. He has an intimate connection to the local area with a cottage on Newborough Lake, and that's how we connected. He's an astronomer at the, what I know as the HIA, Hertzberg Institute of Astrophysics. I didn't realize it's now changed to Hertzberg Astronomy and Astrophysics in Victoria. He's been the associate director of the James Clerk Maxwell Telescope, the submillimeter telescope on Mauna Kea. He started out as a theorist, looking into circumstellar disks. Saw the light and became a practical astronomer. Has moved on into the formation of stars and planetary systems, looking at the assembly of protostars and the internal instabilities that make them vary, which sounds to me like a good opportunity for photometry from us. He's been at the Canadian Institute of Theoretical Astrophysics, U of T, the NRC. Let's see, he started in University of California at Berkeley. So he's been around, works on interesting things. And I think for any of the science wannabes in the crowd, tonight's talk will be absolutely spectacular, looking at the exciting aspects of doing the job and ignoring the hunting for funding, managing graduate students, and all the nasty stuff that comes along with the job. So I'm very much looking forward to this. Welcome, Doug.
Thank you very much. Can you hear me okay? Everything's good? Excellent.
We can hear you good.
Perfect. Let me get my screen up. And so this is a talk I put together about a couple of months ago to give to the Yukon Royal Astronomical Society because they asked me. I will, unfortunately, Rick, I will talk a little bit about funding and later in the talk, and I will actually talk about graduate students, but in the positive manner, because graduate students allow so much more work to get done, and it's so much fun to work with people who are enjoying research at that level. What I do want to say is I put this together as a bit of a fun talk. I want to present some physics. I want to present some theory. I want to present some observations and also give you an idea of how it works for a research astronomer. In having fun with it, I've put it together in the form of a play with a series of acts and scenes. And like any play, there is a little bit of liberty taken. So when I tell you the order in which things happened and exactly what happened, there's a little bit there that's not quite how it really works, but none of the major parts are wrong. They just may be slightly out of order or slightly differently presented than they would be. You know, it's that freedom that you get when you turn something into a historical novel rather than a research paper. So I've had a lot of fun with this. I hope you will too. Before I start, however, I think it's really important to recognize that I work at the University of Victoria in part, and I'd like to acknowledge and with respect the Lekwungen people whose traditional territory the university stands on, and the Shonghis, Esquimalt, and Saanich people who have a historical relationship to the land to this day. As well, at NRC Hertzberg, what some know as the Dominion Astrophysical Observatory and others know as HIA, and is now the Hertzberg Astronomy and Astrophysics Research Center. There we need to acknowledge with respect that the land that we work on are the traditional territories of the Coast Salish peoples. This is very important to note. And then it's also important that the East Asian Observatory and the James Clerk Maxwell Telescope, which is now run by the East Asian Observatory, is in Hawaii, and the telescope is on the summit of Mauna Kea, where the indigenous Hawaiian community still have a strong cultural role and a reverence that the summit plays for them. So we are fortunate to have the opportunity to conduct astronomical observations from that fantastic mountain. And it's a place where, as Rick said, I lived for 2 years as the associate director. And then finally, it wouldn't be appropriate if I didn't acknowledge my funding, which comes primarily through NSERC Discovery Grants and NRC funding, in particular for the co-op program that helps me with undergraduate students. Okay, so with that out of the way, let me get right into Act 1, Scene 1, the great idea. So picture a summer conference taking place in Taiwan. We can tell that it's midsummer because I'm casting no shadow. And so, Taiwan is down there almost getting close towards the equator. And in the middle of summer, you basically have no shadow at all. I'm having a discussion with a colleague. We can call it a discussion. It got a little bit heated. We were trying to understand the way in which stars form. And this is after we agreed to disagree. And the whole point was that we were trying, and this is what conferences do, you get into great debates about what processes are really at play. And the question that I wanted to know was whether or not star formation was a nice, smooth process, or whether it required lots of variability, whether it was very unstable. So what do I mean by that? When we try to form a star, we usually picture a blob of gas in space that has about one mass of the sun in it, in that big blob of gas. And this is an example. It's called a Bok globule. It has the wonderful astronomical name of Barnard 68 or B68 because we come up with awesome names in astronomy. And this isn't a black hole, but it's actually a star, a blob of gas and dust, in part because, and hopefully you can see my cursor, you can see that it doesn't just disappear the light, but you start to see things looking red. And if you punch through in the infrared and look deep, you actually see all the way through, but you only see the reddened stars. And the reason is exactly the same as when you're looking at the sun on the horizon, that the blue starlight doesn't make it to you and only the red starlight does. So we can actually use this to determine how much dust and gas is in the way of the background stars, meaning that only the red light is getting through. And when you do the calculation, it turns out there's about enough material here to make a sun. So this is the type of object that might make a sun. Well, why isn't it making a sun? What is it sitting there? The reason is that the object itself wants to come together due to gravity. Gravity wants to pull it down. However, it's got pressure inside due to the motions of the particles, and those keep it up. And basically, if you don't have enough mass and you have enough motion, you will stay up rather than collapse. So the standard picture, which we show all the time in every science talk, is the cartoon that says, I've got a big region. These would be a molecular cloud. And inside that molecular cloud, where there's gas and dust, I start to make little puddles. The puddles, if they get enough mass in them, gravitationally collapse because they get too much mass to be able to be held up. The material falls in, but if there's any angular momentum, any spin, and if there are any magnetic fields, anything that breaks symmetry, you end up making a disk of material and building a star at the center. And around the disk of material, you build these giant outflows, which get rid of excess energy and excess angular momentum. With time, you run out of cloud falling in, and you're left with just the star and the disk and maybe a bit of an outflow. And then the disk goes away, and we think it makes planets. We think that's where the planets form in that disk. Lots of things make sense, and you end up with a star. Now, the question, as I said, is this happening in a smooth way? Is this like the water flowing over Niagara Falls, where it just keeps going and going and going? Or does it happen in an unstable way? Think of avalanches on the West Coast, where the snow drops into the mountain, stays there until it gets unstable, and then falls down and then builds up again until it gets unstable and falls in. So what we're curious is, if I want to make the star, this material falling in, does it just fall in smoothly, or does it come in bursts episodically? So the reason why we were thinking about this was that a space telescope called the Herschel Space Observatory had just flown, and it was looking in the far infrared and trying to understand star formation. Why the far infrared? Because when we're forming stars, they're inside these molecular clouds, and most of the time you can't see them in the optical. You can't even see them in the infrared. You need to go to the far infrared to be able to see the energy coming from the stars that's getting out. And this is just a picture to show you an individual. This is an optical picture and you can't see the hand, but when you look in the far infrared photons get right through this black plastic bag and you can see the hand very, very well. So we were using a telescope called Herschel. It was making these beautiful pictures. This is a picture of Orion, what it looks like in the far infrared. And if I blow up the picture, you can see where individual stars are forming. And you see them as bright, bright infrared emission. If they're forming smoothly, that bright infrared emission should stay about the same brightness over time. And if they are forming episodically due to events, then that energy coming down will come in bursts, and we should see these things flicker, at least to some level. So someone mentioned photometry. That's exactly what we want to do. So we worked hard, my colleagues and I. We put together a proposal. We said, let's use Herschel and take a second epoch and compare them. We worked really hard and the project was rejected. Too ambitious. Okay, this is often what happens. Expensive telescope to use. Lots of people wanted to use it and they said, too ambitious an idea, when chances are you're not going to get anything. Okay, so back to the drawing board. Oops. Oh, there we go. Okay. So back to the drawing board. We said we wanted to do this in space because the far infrared doesn't get down to the ground. It gets absorbed by our atmosphere. So we can't do it from the ground. What else could we use? Well, what about observing from an airplane? We could try that. And it turns out there is an airplane, Sophia, a 747 with a big hole cut in the back where they've put a telescope and you can observe. So we put in a proposal, we got the time, I even got to fly. I got to take off in the cockpit of a 747 and then sit there with the pilots for much of the night. Just for everyone's sake, thinking about observing, this is really fun because if you want to observe with this telescope, the airplane has to go in the right direction so that you can actually look. You move the airplane when you want to observe somewhere in the sky because you can't move the telescope around. And so we had to come up with a very detailed flight path that flew us all the way up to Canada from California and then back down to California later on in the evening. So it was a lot of fun, really good, really, really interesting stuff, but the results weren't that great. Why? Well, the problem is that when you observe two images and you hope to find a slight variation, it's hard. You got to look really, really carefully to find the things that have changed between the two images. It's complicated further when the images themselves are faint, when they're blurry, and these are hard to take observations. So we realized after this that we really needed many images, not just two. We needed to look through a variety and see that things were changing, to be able to quantify, to be able to understand it. Can't do it from space because it's expensive. Can't do it from the air because Sophia doesn't fly very often. It's hard to get enough time. So what are we going to do? So we go back to our plot that shows us we can't look here because the light doesn't get out of the molecular cloud. We can't look here because it's too expensive or not enough flights. Well, what if I looked at the beginning of the radio? What if I looked at sort of the microwave part of the spectrum? Maybe we could do it there. It's not as good a signal, but at least we can do it not necessarily from the ground, but from mountains. Enter the JCMT. So the James Clerk Maxwell telescope is the biggest single dish submillimeter telescope in the world, still to this day. It's over 30 years old. Canada used to be a partner in the JCMT, and when it was, I was the associate director for the final few years. The telescope is designed for survey science, which is what we want to do, meaning we should be able to get on the sky many, many times a year. And it had the best camera ever built in the microwave. Okay, submillimeter for those who are experts, microwave for everybody else. Disadvantages: it's hard to observe with this telescope. Observing with the JCMT is like observing with an optical telescope in the middle of the day with the telescope on fire, because everything is glowing everywhere. The sky is glowing, the telescope is glowing at exactly the wavelengths I'm trying to observe. So this is hard. It's not easy at all. Calibrating the data is really, really tricky, and it's unclear whether the microwaves will be good enough for what we want to do. Thankfully, I had a great graduate student who worked on the calibration, and thankfully, I had a great graduate student who worked on the data. So here's another picture of the JCMT. By the way, note that we usually have the world's largest piece of Gore-Tex between us and the sky. Like that plastic bag, the Gore-Tex lets through the light we're interested in, but doesn't let through sunlight so we can observe during the day, because why not? It's already hot. And secondly, we don't have to worry about the wind. So usually this is a very rare picture where they took the Gore-Tex away so that you could see the telescope. So here are some pictures from my time living in Hawaii to make everybody feel jealous, you know, visiting the volcano, at home where I live, the food that I ate, the view from my office window. But before you get too jealous, this is what the coastline of the Big Island looks like on the side, the Hilo side where I lived. So not really good swimming. And just because it actually matters, here I am in the dome on the last night that Canada was a major player in the telescope, when we were handing control over to the East Asian community. Okay, so Act 2, Scene 3, we get a surprise only 1 year into our observations. I have been waiting, and this graduate student in Korea contacts me and says, look, Doug, there's an object that's changing in brightness. We're actually seeing it. You're looking here at months. They're basically one image taken each month, and it turned out that one of the sources in that image was actually varying in brightness on the time scale of a year. This is interesting. In fact, it was really interesting because when she observed it, this is its light curve in time, so this is how bright it is as a function of time. She noted it got bright just before Christmas. And then, of course, like all good observations, the source went behind the sun, so we couldn't look at it. And we had to wait until about February, when it came back out from behind the sun, it was even brighter. So this was fantastic. We found an object that is varying in brightness, and is varying in brightness on timescales of years. What's going on? Well, we've thought about it a lot. It looks like something is stopping that material from falling onto the star. Think more like the avalanche. Material builds up, stops, and then it has to be dumped on. And what might stop it? Well, maybe in the disk. This is an older disk. This is a different disk around the star called HL Tau. But these disks have holes in them that are very reminiscent of planets. So the initial suggestion that we had was that maybe there was a planet in the system that was blocking the material, so that as it flew, as it basically slid in through the disk, it got stuck and it could only come across every once in a while. That was the idea that we had. I'll come back to that because that's the physicist, that's the theorist in me trying to get out and trying to see what's going on. Okay, we had another surprise. My other graduate student, my Victoria graduate student, who had just left me to become a support astronomer at the telescope, he found an object that wasn't there in 2016 on the 20th of November, but was there 6 days later, really bright, and then 2 months later was gone again. Now this really confused us, and we thought long and hard for what might be going on. In fact, I checked to make sure it wasn't an interloper, like a planet going through the field or an asteroid going through the field. Because it turns out a very famous astronomer once found a supernovae and then had to retract it the very next day because it was Mars. He'd forgotten that between the time he'd looked at the one part of the sky and the next time he looked at it, Mars had moved into that part, and he thought it must be a supernova. We didn't want that to happen. So we showed that that wasn't the case. And then all these little squares are older stars with disks around them that are known in the region. They just aren't visible in the submillimeter because they no longer have this enshrouding envelope. So we looked at our image again, and that one night of data, we broke it in. Our observations are usually 30 minutes long. So we broke our observation in 5-minute chunks, and we watched the source decline 50% in brightness in half an hour. Now, if you think about it, you know how long it takes for something to cool. If you put a pot of water on the stove and make it hot and then turn the heat off, there's a length of time it takes to cool down that has to do with how much heat it has and how much surface area it has. It's really hard for astrophysical objects to cool down in half an hour. So we pretty well could rule that out. And instead, we're convinced that what we saw was a giant flare like you get on the sun, only billions of times brighter than anything on the sun. And the argument that we have is that it's not just coming from the sun itself, but it may very well be magnetic reconnections between the star and its disk, where you have a lot more energy that can be given off. That's our theory. There's a lot of other people who disagree with this theory, but that's our theory. Somehow you've got to get all that energy in order to be able to make this. And the best explanation I have is that I'm using the energy from the disk. Okay, I want to take a pause here and show you a movie, because any good play has an intermission. This is when you'd go get ice cream, etc. But hopefully I can show you a little movie. This is a numerical simulation of stars forming in a molecular cloud where the whole cloud is gravitationally unstable to collapse, but you get localized collapse to individual objects. The image on the left is showing you the density. The image on the right is showing you the temperature. So you see how the disks get hot because there's a star in the center. And what you really want to see is just how dynamic these systems are. On the time scale here, which is time scales of, 100,000 years, a few 100,000 years, you can really see that it's a dynamical process. You can also see that inside these little disks that are being formed are incredibly dynamic. Don't believe this as reality. There's too much physics missing. There's too much that goes into these models to try to make them interesting. The physicist is trying to understand the process, and I'm trying to give you an idea of the process by having you look at this as well, not have you think that this is telling me exactly how stars form. Okay, let's go back. Act 3, Scene 1. Let's contemplate where we are. We've now been observing for 4 years. It turns out that that one variable I showed you isn't the only variable. We see some sources that are getting fainter, perhaps with a little bit of a twist as they get fainter. We see some that look like they're getting fainter and then brighter and maybe fainter again. We see one that has this very interesting bursting event. Since I made this plot, it's now gone back. It's up here now. And we see other ones which, maybe also look a little bit like something's going on. Hard to tell, but we clearly see variability. In fact, 30% of the sources that we look at are varying. And the reason why it stops at 30% is probably because we don't have the calibration so that we can see things that are varying a little bit lower than that. So these objects are really doing interesting things. And they're doing it on year timescales. The time scale from here to here is about 4 years. So whatever you're looking at, those variations are on years timescales, which suggests interplanetary scales, right? The time scale for the Earth to go around the sun is a year. It's what defines the year. So year timescales are a very appropriate thing to think of an astronomical unit or so. So we think maybe we're looking on at what's going on in the disk. We don't yet think we have planets, but we think we're looking at what's going on in the inner disk down on the scales of 1 AU or maybe a little bit smaller, the size scale of our inner solar system. So to get back to the cartoon, remember, we thought we had material falling in. We think we're seeing it fall in. We're seeing a variability, but the variability seems to have a modulation of few years, which suggests that it's related to the inner part of the disk. So what are we going to do? Let's go and look at this with a few other types of eyes. The first type that we looked at was the near infrared. So remember, I can't see the far infrared from the ground. I can see the submillimeter. I can see the near infrared. Maybe in some of my sources, I'll be able to see a little bit of near infrared emission. And that will tell me a bit more about the star. The near infrared's around here. It'll show me objects that are warm is what I get a lot of near infrared emission from. So let's see what we can do with the Gemini telescopes. Here's a pretty view from the summit of Mauna Kea. And we looked at that variable that I found, the one that we found first, the one that we said now actually has a periodic light curve. And it turns out that in the near infrared, it has a very periodic light curve. This is a phased up light curve. It repeats over and over and over again with 1.5 year periodicity. And that's really cool. What's really bizarre is if I look at its color in the infrared, it turns out that it gets really red right at the time it starts to get bright. Now that's unexpected. Usually you expect something as it gets brighter to get bluer. Why? Because you expect as it gets brighter, it gets hotter, in which case it gets bluer. Hotter stars are bluer. Or you might imagine that what made it dim was like going down across the horizon was a lot of atmosphere, and that extincts the blue light and again makes it redder. But here we were getting redder while it was getting brighter. And that was really bizarre, but led us to a toy model where we actually think that the inner disk puffs up as it puts material onto the central star. So when it gets bright, because it's dumping material onto the central star, we think that it gets puffed up, and the light that we see, remember we're over here somewhere, we see it through the disk, and so we see a reddening. In fact, that explains a whole bunch of things that I don't want to get into here, but it was wonderful because it allowed me to write another theory paper. And so it allowed me to go back to my roots where I talked about what was really happening in the system, as opposed to just the observations. So this is key, because the reason we do the observations in astronomy is to allow us to make that connection back to the theoretical work that's going on. Okay, so that was a lot of fun. What else can we do? We went to ALMA. Now, ALMA is a fantastic telescope down in Chile, which I had the wonderful opportunity of being one of the Canadians involved with helping make this a reality. So this telescope is in northern Chile, on the Atacama Plateau, part of the Chilean Andes. So this is up at over 2,000, 3,000 meters above sea level. And each of these telescopes is basically the same size as the JCMT. And there are 50 of them rather than just the JCMT. And by spreading them out and using the magic of interferometry, they get to give you a very, very high angular resolution. You may remember from optics that your angular resolution depends on the size of the telescope and the size of the light you're using. And we're using light here that's almost 1 millimeter in size compared to a micron in size that one is using in the optical. Okay, so this is just to tell you, where we are. We're actually higher at ALMA than you are on Mauna Kea. And here's a picture of me at the summit when the telescope was being built many, many years ago. So we use this telescope to peer in and look to see what we could get on small scales around the system. So basically to look primarily at the disk and look at what we get. So here's a graduate student who did this. She looked at disks in Taurus. She looked at protostars in Taurus that are forming, and look at the beautiful disks that she finds, from little rings to multiple rings to giant disks with rings, to disks without any ring at all. She found these beautiful rings and beautiful disks around these young systems. My graduate student, my present graduate student here in Victoria, he used archival data. This is very good. Astronomers we practice very much recycling. All the data that gets taken doesn't get thrown out or only given to one person. It goes in an archive, and a smart graduate student can take all that data and reprocess it. And he found all sorts of disks with holes in them. We like to think of them as donuts, very Tim Horton-esque. And these are slightly older systems, but I bring it up because if you type NSERC Science Exposed, this image is one of the finalists for an image contest by our Natural Science and Engineering Research Council. And boy, oh boy, I know that Logan would love you to give it a click and a thumbs up, but you'll also find a lot of other really, really beautiful pictures, including another astronomical one. There's a beautiful picture of a globular cluster from a student, I believe at UBC. So we found these beautiful pictures of disks, lots of structure in the disk, which connects to our notion that we're seeing events occur, which might be related to length scales. We can also look at the outflows. Look at this. This is a picture also taken with ALMA, where you're seeing basically bullets in the outflow, in that jet that's going outwards. And that's important because if the material flowing in is flowing in episodically, then you expect that the turnaround and the energetics that has to go out will also go out episodically. So given that we're seeing these bullets, it's another piece of circumstantial evidence tying the episodic nature of the creation of the star, right? We're not just talking about the fact that it's observed to be episodic. We're saying explicitly that the buildup of the star comes in discretely, that the buildup of the star is not smooth, but it comes in by sort of throwing the clay at it rather than spraying a uniform, slurry of clay down into that central region. So this is fantastic. And I have to say, this has been my most enjoyable experience since graduate school days, because this initial idea that we had that was initially rejected has now led to over 5 years of exciting observations, which has led to fantastic results, which has led to a bunch of research papers, primarily by graduate students. And it has kept us busy as we keep coming up with new ideas to ponder. And in fact, I almost forgot about today's talk because I was reading a whole variety of papers on a thing called flicker noise, which I had never heard of before, and I'm very excited about. So there we go, end of Act 3. We got one more act to go. Act 4, to infinity and beyond. Where do we go from here? So the research astronomer's life is never done. We're never content with what we have because everything that we do suggests we need something new. We need new ways of looking at things. So the first thing I want to do is get back to space. Herschel is done, but I want to get back to space because I want to monitor these stars in the far infrared at the peak of their at the peak of their energy, where they should give me the strongest signal. So I've been working hard for the last 5 years on a telescope called Spica, which would be the replacement for Herschel. And this is an amazing telescope because the idea is to keep the whole telescope cooled to about 6 degrees Kelvin. You might say, space is cold. Isn't that easy? Well, the problem is we've got a sun nearby, and the sun hits the telescope and warms it like it warms the Earth. The warm part of the telescope will get up to hundreds of degrees Kelvin. But even if I put blocking things, I still have to absorb on the blocking part. And so we need to put these cooling fans, and then we need to have pulse tubes, all to keep it cold. This is a difficult thing to do. And unfortunately, last fall, this telescope was canceled, still too ambitious. The Europeans and the Japanese who are leading it said, it's still out of our price range, and it's too complex. Don't fear, we're already regrouping, planning to come back. We will keep this push up, but it's going to take a while. The next thing we've been working on is a telescope we call the FEAST telescope, or the Fred Young Submillimeter telescope. It will go in Chile. It is a bit smaller than the JCMT, but it has a huge collecting area. This telescope has two mirrors, both the same size. It's called a cross dragoon style, and it gives you a field of view that's huge. And we're just going to populate it with detectors so that we can make fantastic maps of the sky. Telescope is mostly for the cosmologists, but those of us interested in nearby the galaxy can use it too. And I'm very pleased to say that this got Canadian funding in 2020. And so this is a telescope that's actually, we're working on as we speak. I've got co-op students working with me on how to scan it. We're writing the research papers on what we will do with it. This is a very exciting. It's led by Cornell and by Cologne in Germany, but Canada will be a major player on it. And then I would be remiss in any talk that I gave right now without mentioning the James Webb Space Telescope. This is the successor to Hubble. Basically, this is going to be an amazing telescope. It operates out to the near infrared and a little to the mid infrared. It's so big it can't be cooled, so it gets harder to use it beyond the mid infrared, but it's a big telescope and it's going to be wonderful. You now probably have heard it's set to launch this winter, and I can promise you that it will give us amazing images and we will learn a huge amount. Okay, scene 2, final thoughts. Let me bring you full circle on this. Research investigations are fueled by conferences and scientific debate. You don't do research in a bubble. There's a lot you can do sitting in your office reading papers, but you need that back and forth with people by having a good discussion, and conferences are excellent for that. This last year has been hard in the sense that that kind of discussion at conferences is hard to do over Zoom. That's been the trickiest part. Patience is a must as a researcher because your good ideas aren't immediately received. In fact, the best ideas often aren't immediately well received because the best ideas often are outside of the mainstream. And so you need to bring people along and get you there. Because of that, luck and serendipity play a huge role. You know, when you're observing, you need to be lucky to get the time. You need to be lucky to be looking in the right place at the right time. You know, we happened to find an obvious source, the first one we got, and everybody agreed with us that we clearly could be finding variables. Very important. The research problems require multiple viewing angles for clarity. We had this great idea. We started it. We started getting photometry of these sources so we could see how their brightness changed. And then all it did was lead you to next questions. So what's happening in the disk? What's happening in the outflow? What physically is going on? How does this connect to planets? All of those research angles, multiple telescopes. Great science needs great graduate students, and great graduate students need great science. This is absolutely clear, and this has been a joy to work on because there's an abundance of data, an abundance of ideas, and we need humans who want to dig their teeth into it. So that's been fantastic. And then finally, as I just mentioned, it doesn't end. You get there and now you want to understand it even better. Now you want to understand the next layer of detail, the better precision. You want to connect it to a broader range of things. More recently, we've expanded our survey by going to a mid-infrared space telescope. We're just having a lot of fun. So with that, the curtain closes. I say thank you, but of course there's always the curtain call. And I just want to remind you of the beautiful images that we're working with, of the beautiful telescopes that I've had the pleasure of visiting, all but this one. And of course, my favorite telescope, the love of my life, the James Clerk Maxwell Telescope. We couldn't have done any of this without our wonderful variable source that we found in our first year. My colleagues are really, really important. And a giant thank you to you for listening. And with that, I'll stop and I'll turn it over in case there are any questions. Thank you very, very much.
Awesome. Excellent, excellent. Thank you so much. That was fantastic. Is there anybody in the audience that has questions for Doug? Please unmute yourself and ask.
I was clear.
We have a Richard Schmoody, member that lives down in the US, said it was an excellent talk.
Thank you.
Enjoyed it.
Ooh.
Doug, can you tell me where FIST is going to be put in Chile?
I'm sorry, I didn't quite catch that. Could you try again?
Yes, where is the, you said it was the Fred Young telescope in Chile. Where in Chile is it going?
Yes. So the Fred Young submillimeter telescope will be just next door to the ALMA site up in the Andes, up in the Atacama Desert. But where ALMA, because it is 50 telescopes and needs to get to be able to move those telescopes kilometers apart because they want to get the angular resolution you get from that interferometry. So ALMA had to be on the plateau. The Fred Young's telescope will be, I don't know if it's this one, but it will be up on one of the summits nearby. So it will even be better in terms of where it is. And the telescope is built. The telescope itself was built in Germany, and it's now going to Italy to be tested. And then it will be cut in pieces and shipped in shipping containers and taken up the mountain.
It's not an easy environment to work in.
No, and in fact, it's even harder because we're going above, I forget whether it's 5,500 meters. Forget exactly what the height difference is, but we're going above a height difference where there are no rules in Chile for how people work at those heights, and they're having to make them up as they go along. And you can well imagine, rightly so, they're very concerned about making sure that the workers are looked after very carefully. So it's going to be very complicated.
Yeah, yes, indeed. I had a chance to wander around the telescopes at the ALMA site on the plain of Chajnantor. It's an otherworldly site. So I was curious.
Yeah.
There are other telescopes that will do submillimeter in the area, for instance, like ACT will do it, but was not suitable for your purposes?
That's correct. So the ACT telescope, we are, in fact, the FEAST telescope, many of the players on it have been part of ACT. The problem we have, and as you said, there are some other submillimeter telescopes. The biggest problem we have is that the big submillimeter telescopes tend to have very, very small fields of view, precisely because it's easy to make a big telescope with a small field of view and not easy to make a big telescope with a big field of view. So the big telescopes give me the resolution I want. They give me the angular resolution on the sky, so the precision I need to see, but they tend to give me a small field of view. ACT gave you a big field of view, but it's a very small telescope. And so I get, it basically gives me a beam that's something like this size, and I can't separate out the individual objects. That's the problem. I need to have a good enough resolution to be able to separate these.
Excellent. Thank you very much.
No worries.
Doug?
Yes.
Richard Schmoody. I don't know, have you considered using the VLA down in New Mexico, or can you get the wavelength you need?
Yeah, that's a very good question. So we have started using the VLA very recently. Let me see if I can go back here quickly.
Okay.
Sorry for doing it this way, but I don't know how to do things. Here we are. So this object here, which had a very interesting brightening event, we have since gone to the VLA to see if we can see any evidence of something happening at the VLA. So for everybody, if they don't know, the VLA is a giant radio telescope in Socorro, just outside of Socorro, New Mexico. It's a beautiful telescope featured in the movie Contact, if you remember the movie Contact. By the time you get to the radio, the pure radio, the signal from the accretion is very, very weak, because in the radio, you're mostly getting non-thermal emission. So we don't expect to see much of a signal of the variability. However, if there are events taking place, they may also be associated with non-thermal events. And so then the VLA becomes very exciting to see if we can understand timing and see what's going on. So I wanted to be able to convert these brightness changes directly or close to directly to mass changes. the rate of mass falling on. And I can't do that with the VLA. But now that we can see that we're getting mass changes, now I can use the VLA to better understand the other physics. So yes, we are now contemplating using the VLA more, but it's because we can use it, and it'll be great for the flares because they are basically non-thermal radio events. I don't know if I answered. Did that help?
Thank you. Yeah, that helped. Thank you, Doug.
Excellent.
Doug, Hank Bartlett here.
Yes.
Just a little more personal kind of question here. How many years have you been involved in this kind of work? And regardless of the cancellations that have come in your way and that, and the lacks of funding and everything else, are you still totally excited and right into this and feel that it is going somewhere?
Okay. So I have been a research astronomer now for so I started my graduate school just over 30 years ago. So I'm an old timer when it comes to working on these things. But this idea goes back the better part of 10 years, I would say, ago, was when we really started talking about it at this conference in Taiwan. I remember it vividly. So this idea is a 10-year-old idea. And like all good ideas, it really took a few years to nurture before it got going. We've now been running the survey for 5 years, and I'm having the best time of my life. I'm having a blast. And this is a really international group that I'm working with. I've got colleagues in China, Korea, Taiwan, Japan, the United Kingdom. You know, this is truly an international project. And I should be really careful. I don't want to give anybody the impression that research funding is not good enough. Research funding, you know, people are canceling things. Why? I put ambitious there to be very clear. We want a lot as scientists. We require a lot to get to the next step. And we do a lot for you in return, in that we test physics, we test technologies, we push technologies, but it's very easy for our eyes to be bigger than our wallets. And it's very reasonable that it's a struggle. And so I'm just absolutely happy that I work with colleagues who are willing to try and try again, and that I work in a country where, you know, I work at the National Research Council. They have my back, they have our full support. If any of you are interested in that aspect of astronomy, the Canadian Astronomical Society puts out a long-range plan every 10 years. We just put out our long-range plan. You can go to the Canadian Astronomical Society webpage and download your own copy of our basically decadal report for what we want to do, and you will see just how ambitious we are. And if there aren't failures along the way that we're not being ambitious enough, and when you're being very ambitious, you need to couch that by also finding things where the telescopes are still working, by talking to your friends who are at telescopes that are working. No, I'm not at all discouraged. I'm having a great time. So thank you for that question, because I want to make it clear that I love what I do. And I think the community, I think the public support us really well. And I hope we give some of it back.
Well, thank you very much. And you must have seen an amazing change in technology in that 30 years.
Oh, it overwhelms me. It really, really overwhelms me. You know, this overwhelms me. The fact that we can sit here and do something this way, that I can give a talk from the other side of the country, for example. Yes, the technology in all ways is amazing.
Thank you.
Excellent. Thank you again, Doug. That is just fantastic. I know I'm excited about just looking at this and actually doing some work on variables right now and reading up on it. So this is quite exciting. I'm looking
Excellent.
forward to see what will happen.
Excellent.
So
Thank you very, very much.
You're welcome to stay for the rest of the meeting if you wish, but if you need to go, we totally understand. You're a busy man.
I will try to stay for a little bit, but at some point I'm going to have to change for dinner because I have a telecon with Korea
Yep.
in about 3 hours.
Yep,
But I'm going to
no
stick
problem.
around for a while because I think there's some astrophotography in that. And
Yes, there is.
I don't do any of this as a former theorist. They don't let me go near the telescope to touch anything other than be in the control room watching the observations. So I look forward to seeing things. Thank you very, very much.
Great. Okay, up next then, we're going to have Robert Bates from the Belleville Center, who's going to give us some astrophotography on globular clusters. Okay, unmute, my dear.
There we go. Thank you very much.
You're welcome.
Before I start, I want to remind everybody that the galaxy season has been renamed to globular cluster season. And given that, I thought I'd present a few of my globular cluster shots that I've done over the last few years. If I can, there we go. Okay. Does everybody see my screen?
We can see your screen, yes.
Okay. Whoops. Okay, slideshow. There we go. Okay. So my job tonight is to show a few of my recent globular clusters. I've been imaging since 2008. I image from the city of Belleville. Of course, it's very light polluted, and the only way around that I can see is to take many, many, many shots. And one of the things I've learned over the years is never throw anything out. So just a note to people, save all your images, save all your darks, flats, and biases, because guaranteed you'll need them again, especially if you image from a relatively bright area. So my mount is a Lost Mandy G11. It's a push 2. I don't have any automatic. I tend to only do 1, maybe 2 objects a night. And so I just align on a bright star, push to my object, center my object, and take 2 or 3 hours of images. And in the wintertime, I can do usually 2. So maybe I'll move to another one. My scopes, my first one was a William Optics Megrez 80 APO. I also now use a Explorer Scientific ED 127 and a 102, and these are mounted side by side, so I can get imaging data from 2 scopes at a time and then blend them together. My cameras are a Canon XS and a T3i. Both have been astro modified to allow the H alpha, the near infrared light to be recorded. And more recently, I've gone to a cooled ASI 294, which has been a bit of a leap for me. I'm not sure if I really like it, but anyway, it's a change for me. My imaging software has been Images Plus in Astrophotography Tool. Processing, I use Images Plus, Photoshop, and PixInsight. PixInsight has been my COVID project. I got it as a gift for Christmas, and it's been a steep learning curve, but it's very interesting to use. But I must comment that Images Plus is now freeware, and if anybody is imaging, it's certainly something to look at, and has some very good sharpening, noise reduction, and that sort of thing. Certainly the price is right. So I want to talk a bit about globular clusters. Globular clusters, of course, are spherical clusters of stars. They orbit the center of gravity of the galaxy and are found in a halo around the core of our galaxy, in any galaxy. They tend to be older stars, somewhere between 9 and 13 billion years old, and they tend to have low metallicity in keeping with old primordial stars. So this is one of my earlier images of M72. And it's only a couple nights stacked together. So it's about 4 hours of imaging time. This is M71 in the upper left, which is a globular cluster, of course. And in the lower right is Harvard 20, which is an open cluster. And they just happen to be in the same field of view. This is one that I've spent a ton of time on, probably 30 hours of imaging time. The globular cluster is NGC 6749, which is in the lower left, and a very faint H alpha emission nebula is up in the center, and a planetary nebula is in the right side. And I'm always intrigued when you can get 2 or more objects in the same roughly 2-degree field of view. Sometimes I'll do a mosaic with 4 or more images to try and get a slightly larger field of view. But you're seeing the globular cluster through the stars and dust of the galaxy, so it's not as pretty, and it's definitely red shifted from the normal globular cluster that you see. My next one is a failure. I was trying to image this one, and when I did my push-to telescope, I couldn't find my globular cluster because the other 2 aren't visible with my equipment. So I searched around and finally found a globular cluster, which is here, and started my imaging. And then at the end of the 2-hour session, when I was processing, I said, "Oh my goodness, where's the other objects?" And then and then I did some research, and it turned out to be NGC 6760. And I recently processed it, and you can see some of the dust stains in some of the Milky Way stars. Anyway, I thought it was at least worth showing that sometimes even with your failures, you can still make a half decent image. And this is another one of my favorites with 2 images in the same field of view. 2 globular clusters. I think that's a globular cluster, maybe an open cluster, but I think it's I forgot to look that up, but anyway, in the same field of view. And this is M15, which is a fairly close globular cluster. You can really see the different colors of stars. M3 again. I've done a lot of time on M3 and managed to sharpen the image to see the stellar details. And this is M5, similar. M12, a little redder than some of the others. they're all calibrated in roughly the same way, but this one has more of the redder stars. M92 is my most recent. It has about 25 hours of imaging time devoted to it. And in the more imaging time, the less noise, and the more you're able to enhance and sharpen the stars. And my last is, of course, M13, which is the Northern Hemisphere showpiece globular cluster. And I did a little close-up, and you can see the propeller in here, which you have to have an eye of faith, but there it is. Yeah. Any questions at all?
That's wonderful.
Nice pictures, Robert.
Well,
Those
thank
are
you.
great
Thank you.
images.
Robert,
Yeah,
can
I
I
have a
just say
question.
that those are gorgeous, gorgeous pictures. As I've been saying in the chat, I started my life as a theorist analyzing globular clusters. How did the stars escape from them? And so it's really beautiful to see. I think one of the ones you showed was M5, right?
Yes.
Yeah, that was one of the ones I looked at when I was trying to understand how stars disappeared from globular clusters. So thank you very much for the beautiful pictures.
Oh, you're very welcome. And I must tease you that up until about five hours ago, I had hair about the same length as yours.
This is my COVID project.
Well, my COVID project the same, and I got buzzed by my daughter today. So
Yeah. Well, my hair got longer than my daughter's, so I can now cut it because that was where I wanted to do. So we'll see.
yeah, yeah. I did a years ago. I did when I was in the trap stage of life. That's when you can't leave your kids alone, and you can't they won't come with you. I built a cedar strip canoe, and then wondered if I could build a telescope. So I ground the mirror and built an 8-inch Dob. And then I sort of wondered, can you take pictures of the stars and galaxies? And and then I just got into it and got a sky shed pod, an observatory built, of course, by Wayne Parker of Glass Tiger fame. And it's just something every clear night, you know, I go out and do it. And I actually did a master's in astronomy again when I was trapped from University of Western Sydney, sort of a correspondence thing when I was trying to demonstrate to the kids how to study and how to learn. So anyway, astronomy is close to my heart.
Excellent. Thank you.
Excellent work, Robert. You're doing a
Thank you very much.
fantastic job. That is great work.
you.
And those the galaxies or the clusters, you could just spend a lot of time looking at them and go down into the levels. That is just great. Does
Thank you very
anybody
much.
else? You're quite welcome. Does anybody else have any questions for Robert?
Don?
Unmute, Don. Okay, we can't hear Don. So
Nope.
we can come back to Don after. So thank you again so much for presenting to the Kingston Center. That is fantastic.
Well, you're very welcome. Thank you.
Okay, next up will be Hank's Sunspot by Hank Bartlett.
Hello there. Okay. Now, share screen. And
Hey, your shirt's just like your background.
yeah, I'm fading right in tonight. Oh, here we want this one here. There. Share. And can I open this to be full? Oh, dang. I did a bad thing there. Hold on, hang on. I clicked the wrong one.
I'm glad I'm not the only one that has these issues.
Yeah, I know. Like, recent documents. Okay, open it up then, please.
Hank, you are open. You're on a new slide number 2. So
Oh,
just go
I
back
am.
to
Oh,
slide number 1.
it's still showing hold on. It's
You
not
just
showing.
added a new slide.
It's not
in
showing
the
that
middle.
to me. Hang on. Don't save. Close that one. Okay.
Reopen it and try again.
Yeah, I'm gonna because I totally screwed that up. This is the layman's talk now. It's the talk from people that don't know what they're doing, but we'll take a shot at it. Hank Sunspot, June 2021. And share screen. And we're going to share this one and share. And I'm hoping that's going full screen. Slide, show, start from first slide.
And
Do we
you
have a full
see full screen audience view? Yes.
There we go. Awesome. I can't believe I did it. Okay. Welcome to Hank Sunspot for the May-June episode of What's Been Going On with the Sun. And yeah, it's getting a little more exciting all the time. I like it. So this month for solar activity from May 13th to June 9th, relative sunspot today, 34. We actually have counts now. 10 active regions over that time with a maximum X-ray of 10 to the minus 4.8, which was a M1.4 flare. 36 C-class eruptions, 3 M-class eruptions, and 20 Hank observing sessions. And there probably could have been 1 or 2 more, but I just didn't get out for various reasons. On the graph in the upper corner here, I'm trying to move the graph in the upper right hand corner. Well, the left hand corner is the first day of the month of our meeting month. The right hand corner is the today, and there's a nice blip there bouncing up that I'm going to talk about a little later. It didn't even reach C eruption, but it is well worth noting, and we'll get to that shortly. Now, as far as, I got to get this one thing out of the way here. Why is this header across the top? Heck with it. Okay. Daily relative sunspot. Some of you that don't do solar astronomy, of course, would not, oh, there I moved it, would not know what daily relative sunspot is. And that is a way of counting the sunspots. And myself, I think it's a little weird, even more than a little weird. And I picked this. There's quite a few different formulas online, but I picked this one, which is relative equals NS plus 10 times NG, with NS being the number of sunspots and NG being the number of groups counted over the entire solar disk. So you 10 times the number of groups. So for this image from 2003, October 30, or August, yeah, October 30, there are 330 is the count. That's 250 sunspots and 80 for groups, which means 8 groups because you multiply it by 10. I'll never understand that. And some of the people that are more into this, like Kim and a few others that get into the science of it all, could maybe explain it someday, but not right now. So I've got down here in the lower right-hand corner, the sunspot groups there were that day, and there is 8 of them, but the one in the lower left is not highlighted. So I'm assuming it had not been named at that point. So I don't know if it was even counted at that point. But I cannot imagine being a solar astronomer before imaging and sitting and counting 250 sunspots and keeping track of them. I guess they would do it on projection and count from there, Whereas if the scope is tracking or they're keeping it reasonably tracked themselves, they could circle the areas as they finish them. But that is it. I would rather say there was 8 groups, 250 spots, but I'm no scientist. Now we've got a solar eclipse coming up. And like I said, this is the layman's way of telling things. This image at the top is an image I took in May 10th, 1994. And it was actually taken, taken with video camera through the telescope. And I was also watching the eclipse at the same time. So this was a really on-center annular eclipse where we get full coverage of the moon's disk into the sun. And it was absolutely beautiful, but I got distracted. And of course, the date is laying over the image, which really sucks. Down in on the right-hand side of the screen of that image, that black and white image, you can see a little bit there, a little bit of white, then black, and then white again, where sun is actually peeking out between mountaintops on the edge of the moon. They're over exaggerated in the image, but this is kind of the cool things you can see during one of these eclipses. And now, tomorrow morning, everybody's got to haul their butts out of bed early if it's clear. And even if it's not, do it. But I'm probably not gonna, because I'm retired. And at 5:36 a.m., the sun will look like this, approximately 58 degrees azimuth. It's going to be rising with about half of it, you could figure, covered by the moon's shadow. And then at 5:40, it's going to have 86.2% of it covered by the moon's shadow, or the moon's body, actually, not the shadow. And it's going to be a fantastic thing to see, but it's only going to be a few degrees off the eastern horizon. At maximum, it's going to be 11 degrees, which is the image on the right, which is at 6:38 last contact. So that's going to be about 11 degrees off the horizon. So you're going to need a real clear horizon. And I know from Kevin's urging, you have all done your homework, gone out, found the best place to see this, and you're going to go do it. And seeing as I don't like lugging equipment anymore, I will just stay in bed and sleep. And then on Wednesday's chat session, I will see all your images, which will be really cool. Unless somehow I really have to get up in the morning, but that's unusual. Now, another part of solar is the ISS transits. And I hope that any of you that are interested, are keeping track of this website. And it is pretty cool. There are 3 coming up this month: ISS transits across the sun, and 1 for me near the moon, and 1 of the solar ones is near the sun. They're only near because I'm not on the center line. Now, taking this lunar one as an example, the image on the left-hand side of the lunar one, for me, it is a near hit, not quite. But for Kim and Kevin and Yarker, they're pretty close to the straight line. They're about halfway in to the middle of it. And they should get an opportunity on the 17th to catch the moon again, crossing. And you can see here that it is a 2.78 seconds, which is a long pass. The very first image that I went to see with the sun was 0.6 of a second. And this would be really interesting. So give it a go. Go to this website. And this is the website right here, ISS Transit Finder. I know you've all seen it before. Different people have mentioned it. But then also I saw recently that people were going, what's that website for the gong? And I've displayed that many times. and people haven't marked it down. So here again is the ISS Transit Finder one, and just put in your location, your latitude and your longitude and your altitude, and then your dates. Pick a reasonable area. I usually pick 10 kilometers within my own home. And the ones that I showed just on the previous slide were within 20 kilometers. And it will calculate what is going on for you in your area. If you've never seen this, even if you're not going to image it, just to see it happen, it is like a little bug crawling across the sun. With the moon, it's a little more diffuse. I did not even see it with the moon until I went to the images after the fact. So with the sun, I did see it. With the moon, I did not, because they're too close. The contrast is too low. So next, a few images from a couple of our members and one from me. Image from Kim Hay and Rick Wagner and myself over the past month. So we're getting out there and we're doing what we can and capturing images and enjoying it. Now, last Wednesday, Bruce mentioned that it was the anniversary of the Venus transit. And sure enough, yes, this month is the anniversary of both the 2004 and 2012 Venus transit. And the 2004 is on the right-hand side, which the image in the upper left, I took with my 4.5-inch Newtonian without any filter at all, because it was a very foggy morning. The other two images are in the SN10, the Schmidt-Newt 10-inch, and they were so exciting at the time, and still are. It was amazing. This time, when this transit happened, it was probably the first time it had ever been recorded, because the previous time would have been 108 years prior, so in the 1890s. Then on the right hand side we have, and that morning, by the way, it was rising in 2004, and in 2012 the sun was setting. And so a nice sunset in H alpha at the top with some beautiful surface filaments, and not much for proms, but some cloud as the sun was setting into it. And then one white light image. We had a little star party for that, or solar star party, up on the hill near our house. And this was through an 11-inch Celestron Schmidt Cass that one of the members, one of the fellows brought. And he had never ever used it before, set it up there brand new, and I captured this image through it. So if you want to stick around for another, well, not 108 years, you can take off that, well, 100 years, just about, you might be able to catch one of these. Now, today was the most exciting and fulfilling in my 17 years of solar astronomy is when I captured this. There have been some pretty decent things, but unfortunately I missed about the first half hour of this. This image on the left is when I first went out, and this was these images are completely unprocessed, and that ring was absolutely brilliant compared to the solar surface. It doesn't look as much here in black and white, but it was just brilliant. And I switched the camera over very quickly and started taking images as this ring began to enlarge and get bigger and start to uncurl from the surface of the sun. As you can see on the right hand side, the lower portion, like a pair of claws releasing, is starting to leave the sun. And it continued, and this set of images takes about 30 minutes. I would love to have just sat there and watched it, and that's it. But I couldn't do that. I had to take images and switch the Barlows in and out and try and get closer images. And it was just absolutely stunning. I messaged a couple of our members to jump on the scopes right away. They weren't able to. Kim messaged me back and said, you know, try and get video. I did get some video, but it's very jumpy, so I'm not going to play that. But it was darker. The video is set to one setting, and I couldn't seem to change it. But amazingly, now here on the left is full, and then 5 times Barlow here, a 2.5 and a 2. And you can see, I almost think this looks like a marlin or something diving back into the water, this long beaked whatever. It's just, but actually it's going the other way and releasing and pulling away from the solar surface. Absolutely stunning. And more. And it just kept on rolling and started to uncurl on the right-hand side. At first, I thought, okay, this is going to go right to a straight bar and then lift off and carry off into space as some of the prominences releasing that we've seen. And absolutely not. It curled back and started to tuck in and come back to the solar surface instead, where it thinned out, dimmed, and eventually probably collapsed. I did not stick around that long to see that. I had some other things I had to attend to. So this is about where it ends right here. You can see on the right-hand side, this is a very longer exposure, giving a little more brightness and detail to it. But this was an absolutely fantastic thing. And if that is the peak as far as prominence eruptions for me, that is just fine, because it was absolutely beautiful.
That is fantastic. Hank.
Wow.
Nice shot, Hank.
It was amazing. It just to sit and watch that unfold. And actually, when I sent the email, Kim, it was still tucked down into the surface. So I get the phone out and I start emailing you guys. And then I go back and what was it? One sentence?
Yeah.
Great eruption going on. Get out there.
Yeah.
And I go back to it and it's like, holy crap, look at how much it's moved. Well, solar never moves that much in that short a time. So I'm sorry you missed it, and Keith missed it. And I would have emailed others, but you know, it was one of those things where if you weren't there right at the time, you weren't going to see it, because it did unfold so quickly as compared to that eruption that I did way back in 2012. It took a lot longer unwinding, but this was just amazing. So that's all from me.
Like I said, Al,
Thank you. Thank you very
but
much.
I had looked at it before lunch and it was just starting.
Yeah.
It was just starting as a little prominence, you know, nothing major. There was the other one that looked like a big shark tooth. And I thought, okay, maybe that's going to do something, but it didn't seem to do anything. But that's
the one below
fantastic.
it I thought was what was going to be the attention point there. And then usually I went back to Gong and I thought, well, Gong usually one of the ones in the States runs high image rather than every 10 minutes. They run minute images, and it'll have the movie. Well, guess what? Today they weren't doing that. So if you go to Gong, any of you that are interested, go to the Gong H Alpha site and don't click on the picture, click on the little play button below, and you can watch. But most of them only have 4 or 5 frames of the whole thing, but you can slow it down and watch the actual and pick up the actual size of the movement, because you lose the idea of the size of this. This thing is going out probably 150 to 200,000 kilometers out into space and then collapsing back down.
Time did you take that picture?
Pardon?
What time did you
it
take
was
that?
about 1500. So it
That's
was
3 o'clock.
after 3. Let me see here.
Yeah, it
Keith.
was after 3:30 when you sent me the email. It was
Yeah,
around
I think
3:30.
it was 3:20. I started imaging until just a half hour later, so about 4 o'clock-ish almost. But the whole thing, if you play it, goes from 1923 to 1913 to 2013 thereabouts on the UT time, and it was absolutely stunning. Wow.
That's excellent.
Okay, thank you.
That's just fantastic. Good stuff. Okay, if there's no other questions for Hank, we're going to move on to Rick Wagner, who has What's Up in the Sky for June and summer of 2021. Need to unmute. Rick. All right.
I'm trying to turn off my video before I start this kind of thing so that, there we go, there it is. Share. The sky this month. June, summer. So we have, I'm going to try and focus mainly on June, but also reaching out into July and August because we don't have any more meetings until September. So the RASC-GA and the AGM are the last weekend in June. The Queen's University Observatory Fast Radio Burst podcasts. I haven't seen a new one up yet, but they do come up with them occasionally. So keep an eye out on their site. They're always very interesting. The BAA events. The radio astronomy group is having another 2 sessions. And then they're having their summer meeting the 26th of June and their autumn meeting on the 4th of September. You can see those start at 6 o'clock and 5 o'clock in the morning for us. So those are for the real keeners, but they're all-day meetings. AAVSO is continuing their series of webinars on Saturday. This is one that I think is going to be very interesting, is preparing amateurs for the next galactic supernova, the snooze alert system. I've already registered with them, so I should get basically an emergency alert if there's a neutrino burst. 2 weeks later, Romp with Betelgeuse, a guide on VSX, which is their search index for variable stars. Something to do with the Bright Star Monitor, which is their collection of small telescopes intended for photometry of bright stars. Something on visual observing, and to close out the summer on the 4th of September, information from periodic star light curves. That's from Gary Billings, a Canadian. The 2 deep sky viewing areas are both closed until further notice, though I've seen rumblings from North Frontenac that there's maybe opening up in the not too distant future to carefully controlled groups. And in fact, there in July, they are going to open their new observatory up there. They've got the 16-inch that was formerly in the Ottawa Centre Observatory. They're installing that up there. So this is the worst month of the year. If you're a nighttime astronomer, you can see on the 22nd of June, just a couple of days after the solstice, only 3.5 hours of astronomical darkness, 15.5 hours of daylight. It's absolutely horrific unless you're a solar astronomer. So events in the sky. Well, tomorrow morning, of course, we've got a partial eclipse of the sun at sunrise. 12th of June, Venus, I think that should be Venus is 1.5 degrees south of Mars.
Yeah.
In the northwestern sky shortly after sunset. Yes, it's Mars. Venus is about almost -4 magnitude. Mars is about first or something magnitude. So Mars is going to be quite dim, but of course you'll have Venus to guide you the way there. On the 17th of June, quite an interesting occultation, 1021 Flamario is going in front of an 11.5 magnitude star. I recommend you watch this, even if you don't try and time it, just to watch the star wink out as the asteroid goes in front of it. 18th of June is our first quarter moon, and a good night for imaging or looking at the lunar straight wall, Rupes Recta. 20th of June is the summer solstice. 23rd of June, Mars goes through the Beehive cluster. That will be quite photogenic in the just after sunset. I'm not sure what imaging will be like. It might be quite low. Full moon on the 24th of June. We have a comet coming up, mainly towards the end of the summer. It'll be in the dawn sky. You can see tracking from Pisces through Taurus and into Gemini in September, so it'll be in the dawn sky at the end of the summer. Galilean moons, mutual events. Because the orbit of Jupiter now has us in the plane of its moons, or the sun is in the plane of its moons, we can get mutual eclipses and occultations between the Galilean moons. So there are 6 that are visible over the next couple of months. Mostly eclipses, but one case of an occultation. And there's actually a group in France that's doing research on these. They can use the photometry, accurate photometry, to further improve the orbits of the moons. And I have some more stuff on that later if there's time. Asteroids this time. So Flamario, then there are 4 asteroids in the early, the first 110 asteroids that are coming to opposition through the summer. So here's the view of the Earth from Flamario. You can see the path of the shadow tracks up through Baja, up over us, and then off Newfoundland and off the disk. And here's the map. You can see the dark green line in northern New York is the center line. The blue line to the upper left is the predicted edge of the body of the shadow. And the red line further to the upper left is the 1 sigma deviation. So you can see it's a pretty well-defined path. And basically all of us are well within the path. A couple of highlights from July. On the 9th of July, in the morning sky, you have a chance to see a very old moon, only 18 hours before noon. And it's going to be very challenging. And in case that's not challenging enough, the 3rd magnitude star Mebsuta, or Epsilon Gemini, will be reappearing from behind the disk of the moon while it's only 3 degrees above the horizon. So there's something to challenge you. 10th of July is the new moon. Here's Venus near Mars. On the 12th, Venus and Mars are close together and the moon is in the picture. The 12th, 13th, and 14th is when Venus is actually at its closest to Mars, only half a degree apart. August highlights on planet Saturn opposition. So Kevin will be imaging it like mad. New moon on the 8th. Jupiter will be visible with only 1 moon. The other 3 will be in occultation or transit or eclipse. The 12th and 13th of August, we have the Perseid meteor shower, one of the best of the year, and no moon this year. 18th of August, another chance to see Jupiter with only one visible moon of the Galilean moons. 20th of August, Jupiter is at opposition. So again, lots of imaging. And 7th of September, just before our next meeting, is new moon. And that's all I have.
Excellent. Thank you, Rick. Apparently you had something you wanted to show, but we want John to do the presentation on the GA first.
Okay.
Hello, everyone. Just want to do a real quick show on the GAs coming up, as we've mentioned here. There are two parts to the GA. If you want to, there's the part where you can buy tickets and take part in some very excellent speakers. It's not very much for members, but the other part is that's free to all the members is the AGM. You can click on that and take part in the annual general meeting to see your board of directors, ask them questions, find out what they've been doing, tell them what you think they should be doing or what they've been doing right or not been doing right. If you have any feedback for them, they always say they would like to have some. So hopefully everybody can participate in that. There is some excellent talks coming up. And all the information you can find here on the GA website. Some of these speakers, some of us have had the pleasure of listening to here in Kingston at the Astronomy on Tap. And they were very, very interesting and knowledgeable and well worth the time to listen to again. And unless there's any questions from anybody, that'd be all.
Kevin here. Who is our main guest speaker for the either Northcott or Hogg lecture? I forget which is coming up this year.
I believe that, I'm not sure what's going on with that.
The Hogg lecture was at Casca. So we don't get it this year.
So we get the Northcott lecture.
And I have not heard anything about that speaker at this point. But like I say, I do encourage everybody to participate in the AGM on Sunday evening at 6 o'clock.
Now, have the reports actually been posted to the website yet? The annual report?
I could not say. Since they've redone things, I have not been going to the web national site too much. It's just too slow for me.
Painful.
Painful is being very polite. Yes.
Okay. That's
I have
great.
not received anything in the emails about reports and stuff being posted yet.
Okay. That's great. No report not ready yet, says Don. Okay. That's great, John. Thanks for letting us know. And everybody, please, this is your chance to say something for the national organization and have them listen to you. Well, maybe, but at least you can get it out there.
Yeah, and participation in the AGM is totally free.
Yeah. Okay. Thanks, John. Okay, Rick, you had something else you wanted to show us?
Yeah. So here we are. Share. So last week on the 5th, I was running the RASC remote telescope in California. And I took out an hour of my time to image Jupiter. why you would question. You ask, is he imaging Jupiter with a 16-inch telescope? And you can see it's not a very pretty picture. And in fact, this is a series of 240 pictures that I took. You can see the seeing varies quite a lot. And I didn't even get it centered because it didn't seem important at the time. But if you watch these are three of the moons. From the right-hand side, it's Io, Ganymede, and Europa. And then Callisto was, I think, well off to the left, out of the field of view. But if you watch Io, as time goes by, it almost completely disappeared.
Wow.
And then came back. So it took a bit of fussing to do the photometry, because my normal tool for this kind of stuff, I normally use Maxim, and it would not track the moons from image to image. So I had to align all the images using Maxim, and then I actually went into Astro Image J and did the photometry, and here's the result. So you can see here's my two comparison stars, which in fact were the other two moons. And then this is Io, as its flux went down to something like about 6 or 7% of its normal brightness. So I was stunned. I was expecting this to be like a 1/10 of a magnitude, 1/4 of a magnitude kind of thing, not 3 magnitudes. But you can see the light curve looks absolutely gorgeous. There's very little noise on it. It's, I'm just, the graph is mislabeled. I'm just learning how to use Astro Image J, but the data is there, and I'm really pleased. So that's what I had.
So any idea why? Was it being eclipsed by another moon? Was it?
Yeah, exactly. Ganymede's
Okay.
shadow was falling on Io.
Okay.
And
So
Kevin-
it's one of the mutual events.
and Kevin
Excellent.
wants to know, were you planning this observation and imaging, or did you just happen across it?
Yeah, I just stumbled. No, I've been watching these things. I've missed a whole bunch of them from home. And this was the last one, in fact, that I could see with the remote telescope. And then there's the other, 6 that we have that are visible from our area through the rest of the summer. So I will continue trying. None of them are as spectacular as this, though. This blew my socks off.
That's excellent. The Astro Image J seems to be quite a powerful program.
Really good, yeah.
Okay, if there's no other questions or for anybody, for the summer, we generally take July and August off. However, we will still be doing the Zoom social on Wednesday nights, and that link will be sent out by our Zoom hostess and host. So we're actually looking for some volunteers who would like to help out. So our next general meeting will be September 8th at 7 p.m. Right now it'll be Zoom because we do not know what's going on at Queen's. We won't find out until August whether they're actually going to open up to outside groups coming in. So we don't even know if they're going back to school or not. So we will have to wait. And if you're not a member of the RASC-Kingston Center, please go to the national website and sign up. We are on YouTube. Look for RASC-Kingston channel. Tonight's meeting will be up there probably tomorrow morning. Twitter, we're at Astro Kingston. Facebook, RASC-Kingston Center group. And so I will leave it open for questions and chatting. And if there's nothing else, we'll say
Can I ask
goodbye
a
to every.
question?
Oh, Sure.
I was
go
going to ask a
ahead, Bruce.
question,
Yep.
a very quick question for Hank. I think he's still here. So in your talk, you talked about a 58 degree azimuth, I
Yes.
think, for the, so I just wondering if you just clarify to somebody with a simple mind, how that translates into the arm of the compass.
That is 58 degrees from true north.
Okay,
That's what I looked up today
okay,
on the horizon. So in the northeast, east-northeast, or
okay,
whichever way you want to look at it, 45 degrees would be northeast. So it's
We'll subtract
13
12
degrees
degrees.
past that. So it's halfway between.
Add 12 degrees, Mark.
Subtract 12 degrees.
you
And
add 12,
Kevin says add 12 degrees because magnetic north is to the left of the geographic North
Yeah.
Pole.
Just click your phone to non-magnetic.
okay,
Don't
right,
get into that whole thing of declination, all that.
okay, good,
Too confusing.
yeah.
Just
And so
know
that's what,
on your phone there should be magnetic north and north.
and so
Just
that's
use
the
north
direction for tomorrow's
and go
eclipse,
58
this
degrees.
rising of the sun, right?
Yeah.
Okay, perfect.
Yeah.
Thank you
So
very much.
that should be where, and once it starts to rise, you're going to know it. You know, if you're
Yeah.
55 degrees or 50, I mean, you hopefully will have more than a 10-degree wide area of sky to look at when
Yeah.
you're going, and you will see it coming up. But I hope you're going, and it's going to be awesome.
Well, I'm gonna give it a
Not only
try.
because I've seen a few before, but
Mhm.
by gosh, I'm hopefully not going to miss 2024 because I've never seen one of those. So
Thanks.
you're welcome.
Okay, so I think we'll shut down YouTube now. But if the center members wish to stay